So previously we've discussed double integrals over rectangular regions. Now we'll talk about double integrals over more general regions that are non-rectangular. We'll still partition the region into small rectangles and compute the volume by considering the volume of the rectangular prisms, and take the limit as the delta goes to 0, the area of the rectangles in the region go to 0, and get the volume. So it's still defined in the same way. But now we want to talk about regions that are more general, the rectangular regions, and so they'll fit into three broad categories. The first category involves regions that may be described and bounded by functions of the variable x. So basically we could use equations that you see here, y is equal to g of x, so y is some function of x, to bound and describe the region. The second category are regions that are described and bounded by functions of the variable y. So here you have x as a function of y. And the third type of region fits into neither the first nor the second exactly. So let's discuss the first type of region. These are regions described by functions of x. And so take a look at this region. It really is bounded by some top function there, y is equal to h of x, so a function of x, and the bottom, y is equal to g of x, okay? And if we were to write out this region as some set, we could write it as r is equal to xy such that x is between a and b, and notice that a is less than b there, and y is bounded by, this is y, bounded by these two functions. Okay? So we could describe the region in this way. All right? And when you can describe the region this way, you can still use the iterated integral approach. But first, you must integrate over dy. So we fix x. We fix this second integration. We fix x to some value there. I just left it as an arbitrary x in red. And wherever we fixed x, so when you're carrying out the first integral, you treat the x as constant. Wherever we fixed x, we're going to integrate y from this point here up to this point here. And that's going to depend on where you fixed x. I mean, if you fixed x down here, you're going to get different bounds than along the red line. But in general, for any x that we choose, we integrate y from g of that x that we fixed at to h of that x that we fixed at. The result of this inner integral is going to be the area of a slice of the graph of the function at this red x that we fixed at. Okay, so it's going to be the area of that slice, and that's where we're getting this that's where we're getting this a of x. And then to get the whole volume, we then take that area, multiply it by dx, that's going to be the width of the slice. So the area of the slice is going to be ax. Now turn it into a volume by multiplying by dx, so you're going to give it a width. And then add up all these volumes of small slices from x equals a to x equals b. And now the function here, the graph of the function, you can't see it. Okay, it would be along the z-axis, which points out of the page there. Okay, here we're just looking at the region, not the graph of the function. We'd need a z-axis for that. And something to note here before we move on to an example is look at this purple and blue curve there, the functions h of x and g of x. They really are functions in that they pass the vertical line test, okay? So along this purple curve, if you draw a vertical line, it'll only touch in one place. On the other hand, they fail the horizontal line test. What does that mean? It means that they can't be inverted, and so you can't describe this purple curve as x as a function of y. Okay, but you can describe that purple curve as a y as a function of x, and likewise for the blue. So let's take a look at the example that we have here. We want to express this double integral as an iterated integral, where R is the region bounded by the parabolas y equals 3x squared and 16 minus x squared. Okay? Here's the two parabolas. The purple is the 16 minus x squared. The blue is the 3x squared. And so the region that bounds them, we'd like to know where they intersect to know where the integral over x should go from where to where. So we equate these two parabolas, okay, the y values of the two parabolas, and we get that x is equal to plus or minus 2. Okay, so that's where they intersect. And now we'll integrate over y first. What does that mean? That means you hold x first, so always look at that second variable. That's what you're holding fixed. Okay, so choose some x value that's between the x bounds, so minus 2 and 2. Just choose one. Throw a dart there and choose one. I'm going to choose this right here. Okay. Now, where do I integrate y? As I'm moving along the y-axis, where do I integrate it for that fixed x? Well, I'm going to start here at 3x squared. This x, whatever I fixed x to be, that's the red there. Okay. From 3x squared all the way up to 16 minus x squared. And this x just depends on where you chose to put your x. As you vary it, the bounds will change. I mean, integrating at 0 goes from 0 here, y equals 0, up to y equals 16. But clearly down here, it doesn't. That doesn't work. I mean, if x was equal to 1, you would integrate y at 1 from 3 times 1 squared to 16 minus 1 squared, which is 15. So you'd integrate from 3 to 15 if you chose x equals 1. That's different than if you chose x equals 0. But in general, whatever x you choose, so treat that red x as a fixed, you're going to integrate from 3 times that x squared to 16 minus the x squared. Okay? And then we want the volume we want to compute that double integral above this region. So we're gonna then integrate dx from minus 2 to 2. Okay, and how do we compute this integral? What do we do? What's the key trick there? As we integrate over y, treat x as constant. Okay, just how you would treat 2, treat x while you're integrating over y. So doing that integral, what's the integral of y dy? It's going to be 1/2 y squared. And so that 2 will cancel and you'll get this x squared y squared. Now plug in your bounds. Plug in your bounds where? Into the variable you just integrated. So plug it into y. X just comes along for the ride there. And so we plug in our bounds. Here's our top bound into the y squared function. And here's our bottom bound into the y squared there. And we then simplify. And you get this expression inside here. What is that? What is the meaning of that? What you're seeing here is the function of x, that when you plug in an x, you get the area of a slice. You can't see because the function's actually pointing out of the page there, but you'll get the area of the slice that's above that red line here. Okay? That's what this x is. So if I plug in 0, for example, the area of the slice would be 0. Okay? If I plug in 1, it would be negative 8 minus 32 plus 256. Okay, that would be the area above that slice. And once we carry out that first integral, we now carry out the second integral over dx, and that's just the integral of one variable, and we get 663.2. roughly. And notice that we get a number at the end, okay? So if you ended up, messing up and having y's in here, you integrate with y, you're going to get a y, then you do it with x, and you'll end up with some y there. No, you should get a number, because you are you're computing the volume under the graph, right? The net volume under the graph, so it can actually turn 0 and negative. And we get a number at the end of that computation. You should not be getting variables. So here is the graph of the function that we just computed its double integral for. You could see that at x equals 0, okay, that line x equals 0, the graph of the function is laying on the xy plane there, and that's why we had a area of 0 there. But as you vary x, notice what's going on there, okay? So we start at x equals minus 2, and we increase. We're getting, so that greenish color there, that's the volume we've computed so far. We keep increasing x until we get to x equals 2, and we get the then volume under the graph that you see there.